Welcome you all to this course on diffraction and imaging. In the last class, we have discussed some aspects of space group symmetry. Okay. Today we will discuss it a little bit more further and how we can use the space group symmetry table and the diagram which is given, okay, in the International Union of Crystallography table to construct crystal structures, because finally that is the main aim of the table. Okay. So, any lattice if we consider, okay, and in which when atoms or molecules have been put at some specific positions, then we call them as crystals, correct? The type of symmetry elements which these crystals exhibit depend upon what position these molecules or the motifs occupy in the lattice, correct? So, the symmetry elements which we have considered are rotation symmetry, okay, which a lattice can have, then mirror, right, inversion, roto-inversion. These are all the symmetry elements which are crystallographic point group symmetry elements, correct? That is, these symmetry elements pass through a specific point. So, any lattice point, okay, if we take it, what are the symmetry elements which will be crossing through that point, that is what we are looking at it, given by these symmetry elements. In addition to it, in a space group or in a lattice, we can have a screw axis as well as glide. The type of screw axis and glide, we have discussed it in the last class, okay. These are all the symmetry operations which are possible in a crystal, okay. When these symmetry operations, okay, we combine them with a lattice, essentially what are the lattices? The Bravais lattices are there. The Bravais lattice, essentially when we look at it, there are 7 crystal class systems are there, okay. They are again determined by the type of symmetry elements which are associated with the crystal lattices, okay. In addition to it, even among the Bravais lattices, like orthorhombic if we see, they have a primitive orthorhombic, we can have a body centered orthorhombic, we can have a face centered orthorhombic. Like that, there are also some sub classifications are there, okay. These what we call it as a space lattices, okay. When we combine all these operations together, okay, the number of distinct crystallographic groups which we can have turns out to be 230, okay. Essentially, if just the point group symmetry operations, how many are there point group symmetry operations? 32, right? If these point group symmetry operations, if we try to put it on a crystal lattice, okay, then the number of space groups which we can generate are 73, okay. And in addition to it, there are another 157 space groups are coming. They are coming because each of the axes, like if we take as a rotation axis, okay, in a space lattice, we can have just a rotation axis, or instead of the rotation axis, we can have a screw axis is also possible, correct? Similarly, instead of mirror, okay, we can have a glide is also possible, okay. If we take these symmetry elements also into consideration, then the total number of space groups turn out to be 230. Then another thing also which you should understand is that the number of point groups which we have considered are 32, right? Many crystals, if we consider, inversion symmetry will not be there, okay. But when we measure property of a material, the property of the material always exhibits as if an inversion symmetry is always there, okay. Because of that, there's another classification which is called as a Love classification, okay, under which we can have only 11 groups are possible, point groups, okay. This we will come to it later, but I am just telling that when we measure or when we try to find out experimentally the symmetries, there are some restrictions are there, but there is a way in which these are overcome. Then we had seen that how the unit cell of a lattice could be represented, correct? Then if the symmetry operations are acting on a lattice, okay, depending by, if we take any specific particular type of a space lattice, okay, then we know that this is what the symmetry which it has. Like for example, what we have considered in the last class is essentially P4 we considered it, correct? This is the particular type of a space lattice which we considered, that is P stands for primitive, okay. 4 essentially represents the symmetry operation which is there. In this lattice, if we look at it, 4 essentially is just a point group symmetry, correct? In a space lattice, we could have a glide plane also can be associated with it, okay. Then what may happen is that this can turn out to be P4 M and one mirror if it turns out to be a glide along that direction instead of that mirror, then this is the sort of space group which will be mentioned. What essentially is that these are all the classes in which the crystals form, okay. Then we look at what is the type of symmetry elements which are associated with it. On that basis, all these classifications have been made. Now, the way we can represent it is, one, all the symmetry elements which are associated with these crystals can be represented in the projection of a unit cell. For this, if we construct a unit cell like this, like here, if you see that this is the unit projection of a monoclinic unit, okay, is being shown along the B axis, where along the B axis twofold rotation symmetry is there, right. So this is essentially we take this to be B, okay. This is 90 degree, this angle is not equal to 90 degree, okay. This is what a monoclinic structure is, right. Alpha, that's one angle is not 90, other two are 90, and this exhibits a twofold symmetry, okay. So this projection, if we look along this direction, that is, this is the symmetry axis, then it will be a parallelogram. And in that parallelogram, what all positions at which the symmetry elements are there, that's what essentially it is being, it's shown in this figure, correct? This is one which is shown in the space group symmetry table, okay. Looking at that, one can understand what all symmetry elements are there, at what position these symmetry elements are existing, that also all this information is given. This is the simplest which one can understand, because the lower the symmetry, it is easier to understand. Though cubic system is the one which is, which since most of the metals crystals into one of the cubic systems are an HCP, we think that that's the easiest. From symmetry point of view, if you look at it, I will show you later, that's the one which is very complicated to look at it. But there are two distinct positions. This is one position, this is another position, okay, because this has only a twofold symmetry. That is why it is being shown that if the symmetry is 2, the multiplicity which is required is 2, means that at two positions, non-equivalent position, okay, the motive has to be kept. See, if I keep a motive here, okay, by a lattice translation vector, I can generate one from here to here, right? But unless I keep it at another point also here, by a lattice translation vector I cannot generate it. So then it will have only just, if 2 atoms are going to be there in this lattice, it will not have a 4-fold symmetry. So to exhibit the 4-fold symmetry for this unit cell, one more position has to be chosen, correct? This is what it means. So if I put it at the motivus position, which is essentially at a random point or a general point, okay, which has only 1-fold symmetry, the symmetry of the location is 1, then there are 4 equivalent positions the atom has to be kept. In this unit cell, if you see it, one is kept here, okay, one has come here, one here, and another one here within the unit cell. Others are, if you can see it, it is outside of it, correct? This is the same thing, because I am considering it is a 4-fold. Okay. Suppose along the 4-fold, let us assume that there is a screw axis is there, 4-1. Okay. 4-1 screw axis means we have to, the translation vector is 1/4 of the lattice translation vector, and you displace by 1/4 and give a rotation of 90 degree, correct? That when you do 4 times, we will be reaching the next lattice point, okay? And that symbol is shown this way, okay? That's essentially, for a 4-fold we show the symbol like this, okay? And on this, if we show a symbol like this, naturally this symbol means that it's like something like a which is rotating, correct? Like a screw, that's what it is, that symbol which is being shown. Similarly, here also if you see, a screw axis is there, 2-fold screw axis is there, correct? Yes. If these are all the symmetry elements which are associated with it, that is when a 4-fold symmetry is going to be there. Around each lattice point, if we consider it, okay, if we put a motive at a general point here, okay, 90 degree when we rotate it, it should be lifted by 1/4, correct? So it will come somewhere here plus 1/4, then again another 90 degree plus 2/4, then it will come somewhere here plus 3/4, correct? Then it will come back again. What that represents is around this axis, okay, you assume that this is where the motive has been kept. It has been rotated by 90 degree, shifted by 1/4. So whichever the position it occupies, plus 1/4 it goes up. Because you should remember that whenever in crystallography we mention the position, these are all given in fractional indices, so that we don't have to know what the lattice parameters are exactly, right? So I assume that if lattice parameter is A, B, C, if you take it, the fraction of the lattice parameter with which the distances are measured and given, okay? So that's, so 1/4 it will come here, and another 1/4 if we take it, it will come here, right, like this, and another 1/4 it will come here, then afterwards it will come to this point, right? So this, if you have to mark it, as I mentioned earlier, that's if lattice position is at some particular point, when we put half or 1/4, that means that from the projection plane it is lifted up, shifted up by that much of a distance, okay? That is exactly what is being shown here, okay? And you see between this and this is P43, this is the anti-clockwise, okay? So this is similar to this. What will happen here in this way also we can show what is the other way in which this symbol can be represented. right? Both these symbols, this one and this one, if you look at it, if one is clockwise, the another is an anti-clockwise, correct? So these two symbols are used to differentiate between clockwise and anti-clockwise rotation. Okay, these are all given in the table. You don't have to bother about it. Okay, this symbol. But I just want you to understand. So this is how it looks like. What I want you people to work out is that how it will look like for P42. Okay, what sort of a symmetry which will be exhibited by the same logic which you can apply. Think about it and how the
Won't P42 become twofold?
two.
Twofold.
There's a distinct difference is there between these two. Now we'll just look at if a sample has got a crystal has got a P4 mm symmetry. 4 mm is the point group which is associated with the lattice, correct? So if you take a lattice like this, okay, the first thing which you should have is around this direction, okay, axis, we have a fourfold rotation which is associated with it, correct? Then what are the other symbols? Then there should be a mirror, one mirror should be there like this, correct? Another mirror should come like this also, right? That's what essentially what's going to be there. Is it not? Then that means that this is a fourfold. Okay. How we represent a mirror is this line is made. That's the only way this mirror is represented. Okay. In the plane of the paper, if the mirror is lying on XZ or YZ plane, that line is made thick. If the line is thin, there is no mirror is associated with it. Okay. There are many ways of representation. Those symbols you don't bother about it, but now you just look at what are the symmetry elements which are associated with it. It has a fourfold symmetry at 2 points. Twofold symmetry are there at 2 points, correct? Then mirror is there. Okay, two types of mirrors. Okay, so these are all the positions where an atom or a motif could be kept. The simplest case which we can take it is we assume that we are taking an atom and trying to form a crystal having this symmetry. Okay. Then if we put the atom at this point, okay, then by translational symmetry these points will be generated, okay, all. That's one which we can do, or we can put an atom at this point also. Okay. Both these points have got the same symmetry, which is because here also the full 4 mm symmetry is associated with it, correct?
The dotted lines are mirrors in this case, right?
These dotted lines are glide planes. Glide also comes in. Glide as a consequence of the lattice itself, it is there. Okay. Dotted lines represent glide plane. Okay. Is it clear? See, if I put an atom here, as I mentioned, if I put an atom around a random point here, let us look at the random point. Okay. At a general point, if I am putting an atom here, okay. So around this point, 4 mm symmetry has to be satisfied. So you take first the fourfold axis. That means that one is kept here, another has to be kept at 90 degree around it, another here, it should come, correct? Then with respect to this axis, we have a mirror plane is also there. That means that all these atoms which are there at this position, by mirror they should be reflected. So that means that corresponding to this one here, this one mirror, that comma represents a mirror corresponding to this one mirror. Okay. Once this has been completed, you can see that there is going to be a mirror here, there is going to be a mirror here, correct? So complete mirror symmetry by putting 8 atoms in this fashion. Okay. the symmetry of the crystal, okay, is exhibited, right? So we have just put atoms at these positions. Now the symmetry can be seen. Okay? But what is the position at which you have kept it? At a general point, right? So suppose we wanted to put it at this particular point, then the number of atoms which are required is only 1. Because if you put one atom at this particular point, since an atom has got an infinite symmetry associated with that, this is the point over which all the symmetry elements are intersecting. Is it not? So at this particular point, it exhibits fourfold rotation, mirror, all are there. Since an atom has got an infinite symmetry, that also has got all these symmetry elements are there. So when all the symmetry elements of the lattice and also the motif which we put, if they coincide, okay, then this is what the common symmetry elements between the motif and the atom which is going to be there. Correct? That is what is being exhibited by the crystal. So we require only one to be put there. Suppose we put at this particular point one here, okay, that atom which is put around that lattice point, then it does not exhibit any symmetry, correct? Only a one-fold symmetry will be exhibited. Suppose in a crystal like this, I put at only this position, like here, like here. What symmetry which will exhibit? With respect to a lattice, the symmetry is with respect to a lattice. So with respect to the lattice has got a fourfold symmetry. If I rotate it by 90 degree, okay, these points are only at one point which is there in the crystal, right? So it does not exhibit the symmetry of the lattice, unless other positions also atoms are there. Is it clear?
But it exhibits one-fold symmetry.
Which one? Only one-fold symmetry it will exhibit. That is what it turns out to be. Okay. So this is what it says, that what is the symmetry of this site? This site has got a symmetry 4 mm, okay, and since it exhibits the full symmetry, that site exhibits the full symmetry of the crystal, okay, you require only one atom to be placed, one atom or one motif to be placed at that point, provided the motif has got the full symmetry, okay, symmetry of the lattice. Then at this center also, if we take it, instead of keeping it at that point, if we keep it at the center, then also we can do with one symmetry it is, okay. There is only one atom has to be kept here. Suppose we keep it here, the symmetry of this point is 2 mm, okay. And if you look at it, that means that one twofold is missing, okay. So then one more point we have to repeat it by symmetry, so that it will satisfy the complete symmetry. That is what these 2 points which turn out to be. If we keep at this point along the mirror, okay, if I keep one at this point at the mirror has got only a twofold symmetry which is associated with it, okay. Then the number of points which are required again gets reduced by half. So 4 positions we have to keep it, because out of the total 8 positions for general we have to keep it. That is what essentially it represents, 4 positions which are going to be there. At general point, if you put a motif, 8 positions. So the crystal lattice now can be constructed by keeping an atom, that we have fixed a lattice. In that lattice, okay, in the crystal lattice, atom can be kept either at this position or any of these positions, it can be kept, and we can construct a lattice having this symmetry P 4 mm. Is it clear? This is what essentially will happen, okay. Which is the position which atom will actually occupy, because this is a geometrical possibility looking at symmetry. is decided by the energetics. So generally what will happen if you are trying to keep a single one atom, okay, we take it, and if it's being distributed, what it will try to do is that the position which has got the maximum symmetry always has got the lowest energy also in the lattice. So that's the position which it is going to occupy. Okay. So conventionally what happens is that like all the crystals of metals we consider, like aluminum or copper, we assume that the atoms are occupying the lattice points, correct? That is how we have studied. Okay. These are all marked where are these positions are there. Okay. In fact, something which is very interesting, it is just for information. Okay. You look at this point, this one and this one, if you look at it, this triangle has got the complete symmetry of the unit cell also. By doing some symmetry operation, if I flip it over it by a mirror, I can generate this, correct? See, this full unit cell can be constructed by from the smallest one. This is generally called as, in the crystallography term, what is the smallest asymmetric unit which is required, okay? Because whenever we work on a problem, on a computation you wanted to do it, we always try to make which is the smallest unit which has to be constructed, and then applying some symmetry considerations, you can expand it and make the lattice. That is the easiest way to do it. Okay, that's the one which conserves the energy also. Minimum energy consideration always tells that this is the way we have to go. Here also, if we can get this information, then the complete information by applying the whatever the symmetry, we can generate all the symmetry elements of the lattice.
So isn't BCD the smallest?
Which one?
Triangle BCD.
B?
BCD or ACD. Half of
No,
the triangle.
no, ACB.
No. If you take half of
Or
the triangle.
AC, no, this triangle, that is this one, this one, this one, this one is what completes that full symmetry. Okay? That's all which you have to take it. Okay. So these are all the things which I have repeatedly told. That is general position, some special positions are there. Then site symmetry is associated with each of the position, and the site symmetry decides what will be the multiplicity of the positions in the unit cell which will be there, correct? So this is the same one I had just tried to form, that is we put an atom at this position. This also, if you look at it, this has the symmetry 4 mm, right? I can put an atom with this unit cell here. This also shows the full symmetry, because by lattice translation symmetry, if I operate, one position will come here, another will come here, another will come here. This is going to exhibit the full 4 mm symmetry. Similarly, if you put an atom at one at this position, another at this position, okay, then by lattice translation, these two translation symmetry, when we apply, these two positions will be generated. Now if you look at this also has got the symmetry. Okay. Similarly, if I put it at these positions, also we can generate a lattice having the same symmetry. We can keep the atoms at these positions on the lattice, and then also have the 4 mm symmetry. At these positions also we can put it, have the full 4 mm symmetry. Or if you put it at a general point, this is the way the atoms will be put, then the 4 mm symmetry. These are all the possibilities which are there, where atoms can put it. But which position it will take, as I mentioned, will be determined by the energy consideration. Okay. So if I want to put a motif at this particular position, what is the motif should have? The motif should have the 4 mm symmetry should be there. Right? That is what I had just shown, a motif which is there like this here. If I put it at this particular point, that motif should have a symmetry, because that's I had chosen a shape of a motif which exhibits the 2 mm symmetry. Okay? That's what essentially what is being done here. An asymmetric point, I have put an asymmetric motif. It does not matter what it is. If I choose an asymmetric point, even if I take an atom and put it, okay, since the site in the unit cell has got a one-fold symmetry, at 8 positions it has to be kept because there is no symmetry element of the motif and the symmetry element of the crystals are intersecting. So, the common intersection, if you look at it, is only a one-fold between them. That is why 8 positions we have to keep it. Okay. So, here an asymmetric motif is being taken, that is I have just shown, and when we keep it, okay, around this lattice point, okay, this is how it will look like. If I put it around this particular point, also this is how. Everywhere if you try to see it, within the unit cell how many are there? 1, 2, 3, 4, asymmetric 8 are there, correct? Here also 8 asymmetric motifs are there. Here also, even though we had kept this around 2 mm symmetry, now if you look at the within the unit cell how many? 8 are everywhere you will have. Okay. They, if you look at it, they all of them satisfy the 4 mm symmetry. That is the crystal symmetry is satisfied by the motif, right. So, whichever configuration you put the motif, unless in this specific way they are placed, okay, we will not be able to generate the crystal exhibiting this symmetry. Is it clear? That is what I am just showing it. Okay. See here, this is an asymmetric motif. Okay. We have kept the asymmetric motif at a particular point, okay, and created the 8 positions so that it generates the it exhibits the symmetry of the lattice, correct. Suppose I have a molecule with this sort of a configuration exhibiting this symmetry, okay. That means that it has a 4 mm symmetry associated with it. I can put it at this position. What is the other position in which I can keep it is if I rotate it by 45 degree, this also exhibits that symmetry, right. So, these are all the 2 positions in which a motif cluster can be kept satisfying 4 mm symmetry. You consider this case, it has been rotated by a small angle. Now, what is the symmetry this exhibits? The symmetry which crystal exhibits? 4-fold. Only a 4-fold rotation is there. Not, yeah, yeah. Mirrors are all gone. Though if you look at this cluster is the same cluster of molecule. How you place it? When you place it, because the cluster itself has got a point group symmetry elements associated with it, whether the axis of all the symmetry elements matches with the point where we are keeping it with that symmetry element or not. At that particular point, what all symmetry elements which are common, that is the only symmetry element which the crystal will exhibit. Otherwise, in any lattice, you take an atom has got an, assume it to be a sphere. The sphere has got an infinite symmetry associated with it, right. If you put the sphere around a rectangular lattice, it exhibits only the symmetry of the rectangular lattice, correct. If you put it around a square lattice, it will exhibit the symmetry of the square lattice, correct. Though the sphere has got an infinite symmetry, that symmetry is not what is being exhibited, because what is the symmetry element which is common between the lattice and the motif which we are keeping in, that the symmetry which the crystal exhibits. Is it clear? Here I have taken a motif with a symmetry which is, it has got a mirror symmetry is there. Okay. Now this motif, because what are the ways in which we can consider it, that is what I am trying to explain, illustrate it with some examples. Here if 4 of these motifs, if I keep it around it, correct, it satisfies the 4 mm symmetry, only 4 motifs are required. when we took a motif which has no symmetry associated with it, we required 8, right? Since the motif itself has got a foramen symmetry associated with it, mirror symmetry associated with it, and we are keeping it in a position such that the mirror symmetry of the crystal and the mirror symmetry of that motif matches. So, the number of positions at which it has to be kept has reduced to half, not 8, it is 4. And the other position where we can keep it is here. Okay, by 45 degree we can rotate it. Okay, this I had already explained. So, suppose this motif I try to put it at a position, okay, where the mirror symmetry does not match. That means that I put the motif somewhere here at this particular point. Then what will happen? 8 motifs have to be kept, correct? Though the motif has got a 2m mirror symmetry, unless we keep it at 8 positions, it will not satisfy the symmetry of the lattice. That is what one should remember. Okay. This is for other positions like that Wyckoff positions D, that D, E are positions, and this is the multiplicity what is being shown. Okay. Here if you try to look at it, in this one it is being shown as it has a mirror symmetry associated with it. If we keep it like this does not satisfy. If you look at it, no position is identical. This will not satisfy the fourfold, the foramen symmetry is not there in this. This I will give you some examples which when you work it out you will understand all these aspects. Okay. Now what is most important part of it is that I mentioned everywhere that when some special position and general position is there in the lattice, like here all these positions which are being given, this is one side symmetry, another side symmetry, these are all the called special positions, this is the general position. Okay. Suppose we wanted to put an atom, okay, at some position in the lattice and generate the crystal. Okay. Suppose I put an atom of a particular type in this position. This position means that essentially I am putting an atom in this crystal, one here, another here and another here. Then a foramen symmetry is satisfied, correct? Is it clear? That is the only position which is possible. Suppose the same atom, I try to put it in this position, you know what will happen? That position is also possible. After filling it up, if I try to put it in that position, what happens now? What is the symmetry which it will have? Yeah, the symmetry is has changed. It no more has the same symmetry. Foramen symmetry is not there. So that is not possible. That means that only a particular Wyckoff position you can put an atom and fill. Okay. The same atom cannot be put at another position also. If you try to fill it, then you find that the structure which we generate, the same type of an atom, if I put it at all these positions, it will be generating a lattice which have some other symmetry, not this symmetry. So one of these positions only you can do it, fill it up. Is it clear? Okay. That is what I had mentioned. A atom cannot occupy simultaneously both 1A as well as 1B position, because then the symmetry of the lattice has changed. Another is stoichiometry. Okay. Suppose I put the two atoms are there, A and B. If I put A atom at this position, okay, this is where the A atom has been placed. Okay. I place the B atom at this position. This is A and this is B. The B atom will also, another B atom will come here, another will come here, another will come here. This also satisfies a fourfold symmetry, correct? Now, the stoichiometry of the alloy is AB, correct? This alloy satisfies the foramen symmetry, right? Because A atom alone, this forms a lattice which satisfies a foramen symmetry. Okay. B atom, if we look at it, this has another lattice, similar lattice, which also satisfies the 4 mm symmetry. Okay. These are generally in crystallography we call it as sublattices. Okay. That is, whenever ordering is there, each type of atom we can consider as occupying. A typical example which we can take it is NiAl. If I take nickel and aluminum, okay. Nickel occupies corners and aluminum occupies center of a cube. For this, a simple case if we can take it is that a simple cubic lattice if we take, okay, all atoms are occupied by A atom. So, its space group is a primitive one, correct? If the same atom, because at the center also will have the same symmetry, if you put a atom there, what it will happen? Now it becomes a body centered, na? It's a different structure. So that's what I said, that symmetry changes. So that is not possible. But in that position, another atom I can put it, B atom. If I put a B atom in that position, then the stoichiometry of the alloy is AB, but the symmetry is like in this case P4 mm. It will be a simple cubic only. That's how it happens. Okay. By looking at it, I can make out. That is, if suppose I see that an alloy I wanted to have a symmetry which is A2, AB2. Okay. AB2 means that what's going to happen is that A atom, I fix it. This is the highest symmetry point, right? So that's what A atom has occupied and formed a lattice. Where can the B position can go now? It's only go into the face center. Now in this lattice, that is, here if I draw it, the A atoms are occupying. I'll just put it as a cross to tell the B atom. So the B atoms now has to occupy only the face center. Now if you look at the stoichiometry, this will turn out to be AB2, correct? That is what here also it says. One atom will be there in the unit cell, it's 2. And in this particular lattice, okay, suppose I wanted to make an alloy, okay, with AB3, that is having the space group 4 mm, AB3, is it possible? You look at this table, that if you put, it is just not possible. We can have AB, AB2, AB4 is possible, AB8 is possible, right? ABC4, there are various combinations which you can try. These are all the ways in which you can build itself. Is it clear? Because this table, if you look at it, that AB composition means that one atom can occupy here, another can occupy this position. Okay? That means AB is a stoichiometry. Okay? Suppose in the unit cell, okay, what we wanted to have is that not AB, okay, AB means that it is a stoichiometry which number, the number of atoms in the unit cell, suppose we wanted to have instead of this one, assume 8, that is A4, B4, stoichiometry is AB, okay, but 4 atoms of A and 4 atoms of B has to be there. So how will you go about now? Then if we choose this one, 4 atoms of A can come in this unit cell, and another position if I choose it like this, 4 atoms of B will come, which we can put it at this position. Now again the stoichiometry is AB, but the number of atoms per unit cell has increased. This is what we call it as the molecular formula. That is, what is the total number? Yes?
So you said if A atoms occupy all the 4 corners,
Yeah.
and if it occupies also the center, the
Yeah.
symmetry is still the same, right? So only the
No.
structure is different.
No, symmetry has changed. The symmetry is always based on which type of an atom which we put it. If the same type of an atom, if you put a, like that's what I meant said, you take a simple cube in which, simple cubic lattice in which you put A atoms at all the corners. What is the symmetry which it has? A atom is showing a symmetry which is a simple cubic symmetry. If I put a B atom, A atom at the center, now what is the symmetry which it exhibits? Body centered. So in the space lattice, primitive and body centered, face centered, they are all two distinct Bravais lattices. Now they have changed.
The axis and the rotation axis and the mirror axis are still the same.
No,
Like,
symmetry, how do you define? Symmetry is defined by whether we have an identical position where it goes. So if the same atom, if you put it, the positions are changing. If you put a different atom, still the identical position. That's how symmetry, you have to look from the definition. Okay, that's how the symmetry changes. Is it clear? Okay. So now you see that you can make out what all types of stoichiometric compounds which can form with this sort of symmetry. That also we can find out. You understand that the power of this table is that looking at this table, okay, we can talk about, okay, what sort of a alloy, where if this is the stoichiometry which a material has got, this is the space group symmetry which it has got, then we can tell which positions atoms are going to occupy in the lattice. We can determine looking at this table and construct the crystal structure. Is it clear? So now I have told you about the molecular formula also. That is how it is going to be, correct?
so
Yes.
So atoms sometimes occupy even like alternate tetrahedral voids. So you can occupy half of E or
See, tetrahedral voids, octahedral voids are
They are
what
not
essentially, they are that, it's like this. When I fill up a position of an atom on this one, the next position which an atom can occupy is what you call it as a void. That also has got a symmetry associated with it. I will come back to a crystal structure, how it is done, then you will understand that these symmetry elements essentially represent what is the position, next position, available position which an atom can occupy. That means that once this position has been occupied, the next available position which has got the lowest symmetry is the other one. That is where that atom will go. If that is filled, when we have to put the third atom into it, now that will look for which is the next available position from the symmetry consideration which is free. That is the only position which it can go and occupy. That is exactly what this table also represents. Okay. This table represents from the symmetry point of view. What we have studied is looking at what are the octahedral and tetrahedral voids. Both are identical. From this only that has emerged. Okay. So here what I have done is taken two types of atoms, okay, and if you look at this, the stoichiometry which I wanted to maintain is AB2, okay. So which is the position that blue atom occupies all the corners, and if the B atoms, that's the orange one, that occupies all the face centers, then this will have an AB2 configuration, correct? What is the other way in which it can happen? There are two possibilities are there. The A atom can occupy 4 mm symmetry at the center also. It occupies that, like here. A atom can occupy this position and B can occupy this position, or A can occupy this position, B can occupy this position. These two, both the possibilities are there, correct? We are considering both these possibilities, okay. But if you construct the full lattice, both of them are the same. You understand that? This actually coming from again from a symmetry consideration. Now if you look at the next one, okay, there the molecular formula is, okay, A2B4, okay, but the stoichiometry is, if you consider it, stoichiometry is A2B2, AB2, correct? So there the possibilities which are there are this position or this position, this is one combination, or this and this another combination, or this and this. That's the third combination. 3 possibilities are there, but all of them will have 2 atoms of A and 4 atoms of B, correct? That's exactly what we are considering in all these 3 positions. Now, how exactly that atoms have to be there is which one will have the lowest energy configuration for the crystal will decide which position finally will be the stable position the crystal will occupy. But what the geometrical crystallography tells is that these are all the 3 options which are available to which it can form. Now, energetics is going to decide which is the position, because here you can see that the bond length will be different, na? That finally the bond length is which is going to matter. Here again you try to draw it and see how it is going to be, then you will realize it. A4 B8 is also stoichiometry is B2, but the molecular formula is different. This happens with chemistry also, na? CH2 is there, CH2N you can put it, okay? They will not be that same. That type of a thing which happens here also, because that an example which I can tell you is that you have studied about carbide precipitation in stainless steel, right? What is the type of carbide which it forms?
CR23C6.
Yeah? CR?
23C6.
CR23C6. Here also that same thing which happens, na?
Here one only, but
Exactly like that it will happen.
is odd number also.
How many positions which they have to occupy, that we have to. So how many atoms have to be there now in the unit cell? That's what you have to be done.
So it should be 116.
Yes, the total number of atoms in the unit cell is 116 for M23C6. That will come later and show you the Wyckoff position table. Okay, then you will understand how it's possible. You understand that? I will come back to the same example again. Other one will turn out to be 106 or 108 for M766. So not only the structure, when 116 atoms are there, you cannot put it on a simple just position on the Bravais lattice. Now the number of positions where they have to be kept, the lattice parameter has increased. The number of positions where you can keep it like this, it is going to happen. Is it clear? Okay. Because normally we think that when we understand that carbide is essentially chromium carbide is Cr23C6, this actually means is only the stoichiometry of the carbide. The number of atoms which are going to be there in the unit cell is 116 atoms. Okay, in this ratio it will be maintained. This is what I wanted to make you. Then when we understand, when we have a table like this, the space group symmetry table, looking at this we can fill up and tell that this is how the positions which atoms will occupy. Okay, is it clear?
Sir, the 3 units are there for A to B4 type, right?
Yeah.
If you fill the whole lattice with
Yeah.
any of them, yes, it will generate the same lattice.
You just make out and tell me, find out whether it will happen or not.
I think so. It happens.
It can happen, it need not happen, but try to find out and tell me. And another also, if you see it here, these positions, some of these positions are fixed positions in fractional indices, correct? Some of these positions are given XXZ, right? XXZ means that if that X has some value, Y also will have the same value, Z has another value. But what the value of X is not fixed, okay? But from the symmetry point of view, it can have any value. X can have any value. These are all the things which when we do experimentally, okay, try to do using either X-ray diffraction or electron diffraction or neutron diffraction, try to find out what these values of X, Y, Z will be, we can find out. But the symmetry remains the same. But that X, Y and Z immediately tells you what exactly is the position which atoms occupy, correct? That is what we get from diffraction experiments. That is why understanding this symmetry is important. First tells that this is what the structure it can have. Then when we get the diffraction data, then you try to analyze it, because simple structures, when we work with FCC based metallic systems, it's very simple. Okay. All information is available, but when you are working on crystal systems, okay, which have different symmetry, or like oxides, okay, perovskites, this sort of material, then you find that one has to find out the position, because the charge balance determines at what positions the atom. Sometimes it can be slightly off from these positions also. Okay. Is it clear? Just with this I will stop it. Now if you look at it, how is the information which is available in the literature? Like copper, if you look at into the many of the books which are there, Pearson's handbook and all, if you look at it, it will copper. There are many ways in which these crystal structures are represented. A1 is one which is being followed. Okay. Then the space group symbol, if you try to see it, it is FM3 bar. This I will come to later. And then the number is given as some 225. This 225 is the space group number. That in that space group, if we go, we can see it. And the structure is cubic. Lattice parameter is given. Z is 4. Z is 4 means that there are 4 non-equivalent positions are there. The 4 atoms have to be there. Total number of atoms in the unit cell. Correct? And what are the positions? A, Wyckoff position A, means that the maximum symmetry is always for that A Wyckoff position at the lattice point. 4 atoms are there. These are all the positions where the 4 atoms have to be there. Okay? Like if you see diamond here, here the total number of atoms have to be 8. Space group is FD3 bar M. Okay? Atom positions are 8A, because A position, but 8 positions it has to be there. What are the positions which they should occupy? This is essentially the positions which are taken from the table which I had shown. We have considered the table only for P4mm symmetry, but for all the ones it is given in the International Union of Crystallography table. Okay. Similarly for like sodium chloride is FCC, is it not? It has 4 atoms of sodium and 4 atoms of chlorine. Stoichiometry is one is NaCl, but how many molecules, NaCl molecules are there? 4 are going to be there in each unit cell. So that is what this number is at 4 represents. Okay. The sodium will occupy a 4A position, that is A position but 4 atoms. Chlorine will occupy the B Wyckoff positions, 4 atoms are there, their positions are also given. Like this the information is available, okay, from crystal structure data handbook and all these things, they give this information. This itself could be used to generate data. Okay. But suppose we have to find out how to generate a particular type of a stoichiometry with this, whether it is possible. With this symmetry, what all other possibilities which exist, okay, then using this table we can find out what type of stoichiometry and what type of crystal structures can be generated. This is what essentially we have considered here. Okay. This anyway you can see it here, I will just not leave it. One more which I wanted to show is just the hierarchy of crystal structures. Okay. Normally metals form with either hexagonal or cubic, correct? Most of the metals which form. Then when a phase transformation takes place in a cubic lattice by replacing an atom position in the hexagon by an atom of another type, okay, then it can go to only orthorhombic or monoclinic or triclinic. From cubic it is to tetragonal or orthorhombic or monoclinic or this one, or cubic to trigonal. If it forms to trigonal, from trigonal it can only go to monoclinic. So what is the transformation path when we do some heat treatment? What sort of crystal structures which it can form during order disorder transformation? That also this table essentially tells us that information. Okay. Suppose in an FCC material, an alloy, a hexagonal phase forms. Okay. From this you can make out that it is not possible. If it has to form only by introducing a defect in the FCC structure, you can form the FCC. You know that when a stacking fault is formed in FCC, it is nothing but the structure of HCP. That's the only way we can do it. So if we can go from one to the other, it's possible, but that is always by the introduction of some defects into it. Without that, phase transformation can take only these are all the paths which are decided. So crystallography, when we understand the whole phase transformation, we can tell about, understand from just looking at the basic crystallography. Okay, we will stop here now.
So here it means that hexagonal cannot directly transform to anything. It has to go through ortho.
If at all a phase transformation takes place by a replacement of atom position in hexagonal, it will go to only orthorhombic. Cubic will not come. If cubic has to form, a defect has to be created in hexagon. But in a hexagonal lattice, if you put some position A atom, some position B atom, if you try to do it, you cannot create an FCC structure. You will create only orthorhombic or monoclinic or triclinic structure.
Even if like
Even using several two-dimensional lattices,
Yeah,
by packing in different ways, you can
Yeah.
only have orthorhombic monoclinic.
yeah, exactly. That's two dimensional also, the same way you have the rule which is there. Okay, these are a three-dimensional lattice.
No, I'm saying two-dimensional hexagonal.
Yeah, that means that when you study diffusional transformation, all diffusional transformation, how does it take place? By an atom coming and replacing it in another position and occupying it. In that, FCC to HCP is not possible. Or from an ordered FCC to ordered HCP, it's not possible unless and until it has to be through a defect.
shear or something.
Which one?
What if like shearing?
By deformation it can bypass transformation.
By when you do deform, you are introducing a defect into it. That's essentially what it is. Right? So that's what I meant, that unless you introduce defect, you cannot do that.
Without introducing defects, how do you go about?
That is, if a perfect dislocation is shearing the material, you will not be able to generate FCC, HCP in FCC. Only if the dislocation splits into partial, that means that we have generated a stacking fault, which is essentially a defect in the stacking sequence. Right? Then only it's possible. Which one? Yes, there are many means by which we can introduce defect into a lattice. Yes, yeah, that's possible. Which one? See, ion to HCP, how does it take place? That phase transformation occurs because of what all reasons? Temperature, okay, pressure, okay, and the volume change which is associated, and the composition. Thermodynamically, these are all the four factors, the parameters which are there. Na? Is it not? Thermodynamically, these are the four parameters which we consider. Or entropy, that's the another one which will come. These are all the terms which are going to be there. The phase diagram which you can alter it when you are doing it with pressure, what is essentially going to happen is that the crystal itself is undergoing, not the crystal, the atom itself is undergoing some transformations. That is, by changing the unit cell electronically, finally the energetics, when we talk about which type of possible structure which it can come, is dictated by the electronic structure of the material. The electronic structure is quite often decided by the pressure, temperature, and all these aspects. We can do it. Okay. So there, what we are trying to look at it is that by applying pressure, okay, when the structure undergoes a transformation to, it should have, okay, some sort of a shear or a hydrostatic pressure. It has to undergo some change which it has to undergo. That change is instantaneous. Some of these changes are second order transformations, correct? Okay. But that will not be stable at room temperature, many of them. Like many of these structural transformations under pressure also we can do it. Okay. When we do pressure, what is it which we are doing it essentially? We are displacing atoms sometimes from their lattice sites, correct? It is equivalent to doing a mechanical deformation. That is, a phase transformation can be done in two ways. One, either by by applying temperature or energy to it, heat energy or mechanical energy. Mechanical energy also by giving a homogeneous shear from one structure to another structure, by homogeneously we can transform. Without introducing any defect it can be done. That is, if we take a square, by homogeneously differing all these regions, we can transform it to this shape. Every point is displaced by a particular amount of a shear, right? Now it has become a parallelogram. It is a 2D lattice. This is a phase transformation. This is by applying a shear, correct? This happens under pressure also. Okay. Those transformations are homogeneous shear. Another is introducing defects into the material. That also can happen. The same transformation we can bring it by, suppose I have some dislocations are there like this here which move. Then also what it will happen is that this is the average shape which we will achieve, but if you look at it critically, it will be one, there may be another which might have, right? So if you, but the average shape, if you look at it, the shape change is similar to that of a parallelogram, correct? So by introducing dislocations also we can do it by introducing defect, but another is a homogeneous deformation. Homogeneous deformation which happens under some of this pressure induced transformation also. Okay. But pressure induced transformation, essentially lot of electronic structural changes do take place in the material. Okay. That is a different aspect of it, we should consider it. Okay. Stop it here.